Hey everyone, and welcome back after our short summer hiatus. I'm back here for what we'll call season 3 of the podcast. I don't know if it makes sense to talk about seasons in podcast land, but we're doing a bit of a topic shift here, so let's call it that. We'll be focusing on some of the promising paths ahead for AI and thinking about how to balance the value added from this technology with some of the potential risks that it poses. And that'll start with today's episode, where I'll be speaking with Francesca Rossi, who is an IBM fellow and the IBM AI ethics global leader based out of the TJ Watson IBM Research Lab in New York. Now, much of Francesca's research is focused on deriving insights from human cognition that might help AI systems generalize better, which I love because it's a somewhat contrarian way of thinking about general intelligence, especially in this era of GPT-3, Mu0, and AI scaling that have us think that reinforcement learning and deep learning can kind of do it all. So really looking forward to diving into Francesca's work and her research and her thinking about thinking on this episode of the Towards Data Science podcast. Here we go. Francesca, thanks so much for making the time.
Thank you. Welcome.
Yeah, I'm really excited to talk to you. I think we're going to have a very wide-ranging conversation about a lot of topics here because your work is so wide-ranging. Maybe we can start there, though. Can you speak to what your research and kind of work life looks like these days? What are some of the projects that you're focusing on?
So I'm part of IBM Research. So I join and lead several projects around AI, advancing AI. So in particular, for example, one of them, the largest one that I am leading right now, has to do with leveraging cognitive theories of how humans make decisions in order to understand how to possibly advance AI in those capabilities that even now, with all the computing power and data that we have available, still AI does not have, but humans do have. And in particular, we started looking at the thinking fast and slow theory by Daniel Kahneman to understand whether these two broad functionalities of our reasoning machinery that help so much human being in being adaptable and being able to generalize from one setting to another one, can actually also help machines in getting some of those functionalities. Of course, we know that machines and humans are not the same thing. They have completely different platforms on which to build, or to describe some capabilities. But I think that some of those concepts can be useful in designing architectures and then testing them, in testing such functionalities possible also in machines.
Yeah, I think that opens up this whole really interesting area of discussion and debate in the field where people are looking at, human systems or biological systems for inspiration. And then other people look at that and say, well, wait a minute, why should we be limited by the biological constraints of these machines? And, the flip side as well, this is the one example of intelligence that we have. Yeah. I'd love to dive into that a little bit. Right. Sorry, go ahead.
No, I mean, that's what you're saying is very true. In fact, there is always this in the back of our mind, there is always this question, but is this a bug or a feature? I mean, things that we see, although we have limited, of course, we know that we have limited knowledge of how humans actually reason and even less knowledge about the brain, and the functionalities of the parts of the brain. But what we think we see in how humans make decisions, is this something that is dictated by our limitations? And so if you don't have a limitation, if you have a platform with less limitations, like a machine that can handle much more data and so on, and then maybe you shouldn't use the same structure or the same solution, or is it something that really is a feature, meaning that it's something that allows us to have that? So the bottleneck that we have because of our brain, our resources, is it really bad or good in terms of acquiring those functionalities? So that's always in the back of our mind. But I guess that we want to explore the hypothesis that actually these are good. They're not bugs, but they are functionalities and structures and architectures in our reasoning machinery that we want to experiment with in a machine environment. But of course, the goal is not just to build machines that behave and mimic how humans make decisions, but there should also be to build machines that can help human beings make better decisions, because we know that we have our own limitations. Yes, we can adapt, we can generalize, but we also have limitations. We have a lot of bias that we use in our decisions. We sometimes use our thinking fast when instead we should use the thinking slow, be more careful, and so on. And sometimes we make these mistakes. And maybe machines that know how we reason, they can alert us and so help us, not making these mistakes and not be subject to those unconscious biases.
Would you mind delving into the thinking fast and slow piece? I know this, a lot of people might be familiar with this, but it was, I think it might be new.
Yeah, those are two broad, I mean, there are two very broad methods of reasoning, capabilities. The thinking fast is what we use about 90% of the time to make decisions, which is a very fast, almost unconscious way of deciding what to do in a certain environment. So it's fast, really, in terms of time for human beings, is almost unconscious, almost involuntary. So it's something that automatically comes out as a decision. The thinking slow is more like a careful decision, reasoning about the pros and cons, and trying to understand, what is really the best solution to a certain problem. So why do we use 90% of the time the thinking fast? Because usually many of the problems that we solve every day are within a threshold of cognitive difficulty, so are below a threshold of cognitive difficulties. And if we perceive that, so they are cognitively easy, then we use our, thinking fast. If instead we perceive that they pass that threshold, so they are problems that are more complex, or problems for which we really care that we make the right decisions, then we may resort to the thinking slow machinery.
And so your thinking here is that this, as you said, might be more of a feature than a bug, and something therefore that we might want to explore trying out in the AI context. Right. What are some of the like architectural choices when it comes to AI that you might imagine making on the basis of that analogy? Like what does this make you want to try out?
For example, the very high level concept of an architecture would have, well, first of all, you need to define what is thinking fast and thinking slow in a machine, right. Or at least not maybe to the level of many details, but at least to characterize what is a thinking fast agent, let's call it agent, and a thinking slow agent. So already here you see that it means that I need to work with a multi-agent architecture where I may have several problem solvers. Some of them have the characteristics of the thinking fast, some of them have the characteristic of the thinking slow, and each one is dedicated to solve one problem or another one. So I am in this multi-agent architecture. Then, of course, one thing that I guess you also need is to have another agent that takes care of deciding. I mean, am I going with the thinking fast, or should I go with the thinking slow? And so you need some, what we call the metacognitive or introspection module or agent that plays the role of doing this kind of arbitration. And then maybe to mimic the fact that that system one capabilities just are not deliberately activated in human beings, but they just start by themselves without any conscious, thinking. Then maybe in the architecture that we have in mind, the thinking fast agents, they understand by themselves, without the need of this metacognitive agent, whether they should be they should be triggered to try to solve a problem that comes from the external environment. So they don't wait for the metacognition module to just try to solve the problem. And then once they try to solve the problem and they have a proposed solution, then the metacognitive the metacognitive module says, okay, now the thinking fast agent is proposing me that solution. Should I trust that that solution is what I want, or should I activate a thinking slow methodology? So you see already that you have several pieces, and of course all these pieces need to be supported by some knowledge about, yes, the external problems, but also knowledge about what has been done in the past by this machine, know how which problems have been solved, by whom, by which agent, thinking fast, thinking slow, with which kind of success, because then this is information that the metacognitive module will use in making that arbitration decision.
So that's fascinating. A lot of interesting desiderata there for anybody who's like trying to think how this maps on. I could imagine a whole bunch of different paradigms that would fit in that mold. What do you think of the argument that would say something like, deep neural networks, to the extent that something like this would be useful, you would expect a deep neural network that's sufficiently big to eventually learn this type of architecture all on its own without needing to be, let's say, split up into agents to begin with. Do you think that's a plausible argument, or?
Somebody could say, well, after all, our brain is one big, but actually our brain has a lot of different components that interface with each other and communicate with each other with information and signals that go from one component to the other one. It's not that it's like a big uniform neural net, or in human terms. So, but again, the fact that the brain has this structure doesn't mean that machines have to have the same structure, but the brain is not an example of something, in my view, even though I'm not an expert neuroscientist, of course, is not an example of something that where one big neural net is going to give all the capabilities. It has a lot of structure. So for now, in my view, these various agents that I see in this architecture can be supported by machinery given by deep learning or reinforcement learning or even symbolic logic-based AI. So we don't put any restriction on how you want to implement these agents, and even the way these models of the environment, of yourself, of what you did in the past are going to be updated. So, but I mean, I don't see any reason why we should at some point have one big neural net that is going to give you all this thing. But I mean, again, I don't know.
Yeah, no, it's hard to tell, but it's, I mean, it seems like a good point. We've seen in the past how clever guesses about the architecture of these systems can serve to like really accelerate performance, like convolutional neural networks did for computer vision.
Yeah.
Arguably, I guess transformers move us back in the other direction, but it seems like there's an ebb and flow in this stuff.
Yeah, right. So so definitely, I mean, this is not an architecture that says we have to build something alternative to deep learning or alternative to reinforcement learning. That's not the goal here. But it may help to understand how to complement or augment what is already out there, with the ability really to think about general concepts and to be more, adaptable, which I think is, I mean, overall in the AI community, a recognized need from where we are in AI.
And actually, this ties in, you mentioned a moment ago, you mentioned symbolic logic and those sorts of approaches. I'd love to get your thoughts on like how that fits in, and whether you see them, symbolic approaches to AI, as being compatible with deep learning, neural networks, reinforcement learning, that sort of thing, or are they like incompatible things?
So I think that they can be used. in separately, but they can also be used in a combined way. So, I mean, we have seen many approaches where search algorithms like Monte Carlo tree search are being used together with deep learning or reinforcement learning, and that was the best, way to solve a problem, a specific problem. So there is a lot of activities around neurosymbolic AI, which is exactly, various approaches to try to combine the capabilities of the symbolic and logic-based AI with the more, data-driven, and machine learning kind of AI. So definitely they can be used in combination, and in some use cases, it has been shown that this combining them is the best solution. But I don't see why they cannot also be used in isolation. Having said that, however, so if you use some suppose that you say, okay, the thinking slow is about really searching through the space of all possibilities and then making a decision only at the end. But actually this would, in practice, probably you would not be able, even in a machine, to wait until this huge search is going to finish. So you will have some heuristic functions that cut the search at some point, and maybe those heuristic functions can be provided by the other kind of machinery, which is more data-driven. So it's always a combination. It will never be fully one kind of AI or the other one, I think.
Well, actually, that was really interesting. You just kind of clarified something that I didn't realize I was missing, which is like the definition of system 1 versus system 2, fast versus slow, comes down to essentially the range of different possibilities that these like nodes are exploring. So I guess, more system, the thinking fast system would look at a more limited range of possibilities to come to a conclusion more quickly. Is that the idea?
Well, you mean the system 1, so the thinking fast, one could see it as being faster because it cuts the search much earlier. Mm-hmm. But it could also be seeing as solving a problem which is not exactly the problem that you were given, but a simpler problem. Mm-hmm. So then you give a solution to a simpler problem, hoping that it works well also with the actual problem that you have been given. So, and this I think has been seen that humans do many times. So
underfitting, essentially.
Yeah. So system 1 is like building or reasoning about a very approximate model of the world and what all the features that are relevant for this problem, and trying to get a fast solution to a problem, but sometimes even solving a different problem because that different problem is much easier. Especially, of course, I think this is done when we perceive that this transformation from one problem to a simpler one is not really something that is of concern, because maybe it's not really the value for success is not really very, very high. I mean, usually I think if the value for success were very high, we would not just solve a simpler problem and then hope that it works well for the other problem. I mean, so there are many reasons, but it's not just I don't think the system 1 can only be seen as system 2 where the search is shorter.
Interesting. Okay. And actually this brings up another question, which is when you're looking at system 1, I mean, I imagine you potentially have a lot of different system 1s kind of operating in parallel, solving slightly different simplified versions of the problem they're dealing with, which then raises the question of how do we figure out which one to defer to? Like,
yes,
somehow they have to.
Yeah. So in some sense, in the system 1 area, it seems like there may be parallelism and a kind of a race, parallelism, and then who wins in this race? Which solution do I get? Do I decide to adopt? In system 2, at least in human beings, since it is a deliberate process, deliberate reasoning process, it's serial. System 2 is not, you don't have several parallel system 2 processes at the same time. You just have one at a time. And that again is one of those things that you say, oh, but this is a bug or a feature, maybe because it's serial, because with our brain, we can only afford one system 2 process at a time because it requires all our attention. But it could also be that actually is exactly what you want, even in a machine that has a completely different embodiment. Because one could say, oh, it's because of our body. Our body, we don't have, several bodies to control. We just have one. So because of that, then of course, this careful decision analysis and so on is serial. But so one could say, okay, so then I create a machine that has a different embodiment, which allows more parallelism. It could be, but it could also be that actually it is an important feature to have this kind of bottleneck in the system 2 side. While in system 1, you have these autonomously triggered, agents that try to solve problems and propose solutions to the metacognitive module that then decides whether to adopt them or not.
That's really, it's especially interesting in the context of like switch transformers, which, become a thing recently, where people are building a module that does essentially exactly what you're talking about, maybe in a slightly different way. You have this part of a neural network that's trained to decide to which other neural network you should route a particular problem based on its interpretation of the problem. This seems like kind of in that family of classification.
Yes, with the difference that, again, the metacognitive module, that sometimes the metacognitive module is not even activated. And sometimes it is activated, but only after the system 1 agents have worked. So in some sense, the metacognitive module does not have control on the system 1 agents. It can only decide whether to adopt the solution they propose or not. But if it says not, then it will activate a system 2 agent. So it's not just a switch, because on some of the agents, it does not have full control. They have already worked. When he wakes up, they have already done the job.
Right, like an involuntary flinch just happens without our thinking about it, and then maybe our higher brain functions are left to process the output. Maybe we spilled some water or something, and now we have to deal with it. But interesting. What do you think? And this is obviously going to be much more speculative, but to me, this kind of invites questions about what human subjective experience is and where it enters into this whole process. And when we talk about metacognition, introspection, it's hard to avoid here the specter of consciousness. Do you have any speculative thoughts, just kind of playfully here, about how this stuff might tie in?
The use of the term consciousness is a bit, I don't know, it's a bit possibly misleading, because of course we know what consciousness may mean for a human being, the subjective experience of ourselves doing certain things or experiencing the world and so on. So I don't see that in a machine. But but consciousness, of course, also includes awareness of where we are, and introspection about our own capabilities to solve a problem or not, and reflection about our past experiences to make a decision on the current problem. And I think that these capabilities can be in a machine, so which may be in this big word that we call consciousness. But if consciousness is really the subjective experience, then it is like saying that a machine should have another agent on top of this multi-agent thing that actually can look as if it was an external agent, can look at the whole architecture and reflect upon the functioning of this architecture, which it could be, but I mean, that's
interesting.
That's not what at least for now, we're not trying to build that additional thing. Also because then you're not really sure where you stop going up and up,
Yeah, right.
But so that to me would be the subjective consciousness experience of self, to be able to look at yourself and to build a model of yourself as just like you make a model of somebody else. So you make a model of yourself so that you see how limited model, approximate model, and you see how you reason, how you make decisions, But I think that some form of it, meaning not having experience and knowledge about your past experience, about the model of the world, about your own capabilities, that can and should be embedded into a machine.
Okay, that's really interesting. This is actually the most concrete, I think, definition of consciousness I've heard from somebody in like computer science before, as a module that would exist on top of a specific architecture. That's actually, it's kind of interesting that you have that theory, because it does become so almost tied to experiment, tied to what we could do in practice. Does the consciousness piece inform your thinking about kind of AGI and how we would approach that, or is that sort of strictly a speculative thing that you're
Well, no, not really, because I mean, for now, as I said, we only envision this partial awareness, if you want to say,
right.
if you want to call it, which is maybe part of this big word consciousness, which is about building a model of the external environment, building a model of yourself in terms of your past experience, and using those, and possibly also a model of others, machines, people, and so on. If you are in an environment where you're not isolated, you're not by yourself as a machine, but you are with other machines and with other but maybe that's also in the model of the external environment. And so using this information to really make all these pieces interact with each other and allow them to make the best decisions. So there is a form of awareness of what happens externally, what has happened externally, and what has happened internally, but limited. I mean, I wouldn't say that is the form of consciousness in terms of building a model of yourself and so on. But I mean, I think that that's one step, maybe then later we'll think about the future steps.
Yeah, it's a really interesting hypothesis. Actually, one thing I did want to ask you about too, because you wrote about this in a paper that I read, where you talked about this idea of common sense as being perhaps, I'm not sure. I mean, do you think of common sense as a special class of cognition that it would be especially difficult for machines to develop? Or like, what's your thinking broadly about the definition of common sense and how it applies to AI?
Well, I mean, it is tied, in my view, to how good you can build a model of the world, both common sense and causality, a model of the world that includes causality, causes and effect. So, and how you learn those causes and effect in an environment, how you transfer cause and effect relationship from one environment to another one. So that still is something that I think in my work, it needs to have a lot more work and a lot more thinking and more exploration and testing. And also, it's important that, of course, you can build this whole machinery, but you also need to have a very good testing environment that allows you to test whether you can actually exhibit some common sense reasoning or causality learning and so on. So the choice of the testing environment and the platform in which we're going to test the capabilities of the machines is also very important in that respect. So yes, common sense and causality are things that our system one can handle. Okay, so our system one, in fact, if you look at Kahneman's book, system one is the hero of the story, not system two. So system one can make fast decisions, have a good approximate but good enough model of the world, understand causality, understand common sense, and make good decisions most of the time. With machines, I mean, I don't want to equate system one to machine learning approaches because that's not necessarily the case. But with these data-driven approaches that seems to be more similar to kind of less reasoning and logic-based approaches to make a decision, still, that's those capabilities that our system one has, that they're not really there, as a core component, common sense or causality. So those things are things that are still, not really advanced, I think. Although, I mean, there have been a lot of progress in some specific examples.
Right. And this is where I think there's this like fascinating question about scaling and how AI scaling actually starts to flirt with, common sense and causality and all this sort of thing. We've seen with GPT-3, for example, you start off with, when you train a natural language AI, very simple babbling, like it figures out, oh, okay, these words or these letters even are together quite often, so I'll put them together and so on. And gradually the sentences become coherent and then the paragraphs become coherent and so on. And then eventually you do get with GPT-3 this, like, it seems sometimes to be quite causally consistent.
Yeah,
do you think that's...
But first of all, sometimes. Yes, the word is sometimes. So what I'm saying is that more generally, if I had to say, okay, is this system exhibiting that particular form of intelligence, understanding the story, causality, what are the important topics there, entities, and so on. And I would expect that system to, yes, maybe do things that look very reasonable, but also then to allow me to ask questions about that, so to understand whether there is I mean, it's difficult to use the word understanding, because what does it mean, understanding for a machine? Does it mean that you just observe the, people would say, just observe the behavior. If you're satisfied with the behavior, that's it, no? So, but I would expect that then I can ask questions about why, about what was generated, for example, and have reasonable answers, not just sometimes, but, that gives me certainty that the causal and effect reasoning and the common sense reason is there, even if I don't see it explicitly in pieces of code that say, okay, even if I see this huge number of parameters and so on, so I don't see exactly where, but at least externally in the behavior, in the interaction, I would like to see that there is some internal knowledge of those two, of common sense and causality information.
Yeah, that's the interesting thing with the way that we're approaching intelligence currently, like through the AI scaling strategies, is like the failure modes of these technologies are very different, or seem different, from the failure modes of human reasoning, which kind of leads us to, it's tempting then to say, oh, okay, well, it's not doing real reasoning, or it's not genuinely kind of understanding the material. I'm really curious about, like, what would happen if we were to apply a kind of causal reasoning test like that to a human being in turn? Because I imagine that, for the average person, causality isn't, we kind of have to some degree an intuition about it, but we tend to fail with more complex problems. So it'd be interesting to see if, if that starts to go.
That's true. I mean, that's true. That sometimes with humans, they do not have to pass the same bar that the machine, but suitably trained and humans, we trust to put them in situations where there is the need to make very high stake decisions. I'm not sure that I would trust a machine that sometimes looks to make reasonable things, outputs and behavior into high stake decision settings.
Right.
So I don't think we are yet at that level, even though, and since there has not been shortage of data and computing power, so then one question would be, but is that really the scaling approach? Is that really the right approach to achieve those capabilities?
Well, and it calls into question, as you, I think you raised in one of your papers, this question of how we evaluate NLP based or just generally AI systems, like what metric do we use to say, okay, this is safe enough, this is good enough? Obviously, with self-driving cars, that's becoming a real thing already, and who knows what other domains as well. So do you have any thoughts about what principles we might use or intuitions we might use to kind of guide our reasoning in terms of evaluation of these models?
Well, I think that in some scenarios, you want to, okay, there are tests that you can do and thresholds that you can use, and you say, okay, like even with normal cars or current, human-driven cars, you have tests that you do before being able to deploy a new model, right? So you have this test that car, goes around, it doesn't have to turn on its head and so on. But so there are tests, that's fine. But I think that with a machine, you should also be able to, especially in some deployment scenarios, to use like to put in place some way to get to the rationale of making certain decisions. So to the so-called explanations, whatever that explanation means in the different settings. So meaning, okay, you made this decision, tell me what are the features that were most responsible for making these decisions, so that you may understand that really what went into the decision was things that you would judge as the relevant ones, or maybe completely different set, because if they are completely different, then I'm not sure that you want to trust future decisions from this machine. So explainability certainly is very important, also because if you deploy a machine in a scenario where it's going to support a human being making decisions, then that human being is not going to, how is he going to trust and follow what the machine says if it doesn't have some idea of how the machine is really making decisions or providing recommendations? So to me, the machine must be capable in some approximate way to provide a form of explanation. In some scenarios, I understand that if you get a machine to do book recommendations, okay, maybe explainability is not that important, but if you want a machine to make suggestions or recommendations for some therapy for a patient, then you would like to be more careful and say, okay, let's give me an explanation. But of course, the explanation has to be tied, very approximate, but tied to the actual, input-output relationship, of the machine.
Analysis makes
definitely a mix of tests and these other forms of more reasoning based, I think, capabilities.
Yeah, that makes a lot of sense to me, especially given, so I remember back in the day with self-driving cars, the big sort of, the metrics game was to say, well, look, if these cars kill, let's say, fewer than 10% of the people that a regular human driver would, then we have a moral imperative to put these cars on the road. But at the same time, at least it seems to me, and I'd be curious to get your thoughts on this, that one of the challenges with that line of reasoning is that it discounts the possibility of kind of out-of-band events where by some freakish coincidence or accident, all cars like simultaneously drive off the road or into the closest building because of some weird bug in the system. And because those bugs may show up very infrequently, but have a huge impact when they do, these kind of short-term time estimates of like, oh, this week, automated self-driving Tesla killed 1/10 of the people of a human driver become a little misleading. What are your thoughts, I guess, on that kind of aspect?
The bottom line is that these, measures need to be decided not by a company, but by a society. No, the society, all the stakeholders together need to decide what are these measures and the thresholds that allow us to put, whether it's self-driving car, but also any other things in the market. So to me, so that's the most important thing, Then of course you can say, okay, so but then these measures, whether they should they should look at how machines are doing things, or how they should be related to what humans would, the consequences of human driving,
right,
comparison, or it should be intrinsic to something that are properties of this machine, independently of what happens with the humans. Yes. So there are these two alternatives, I think. So whether you say, okay, whatever machine is that, I don't care, but if it's better than a human being, I would use it. But of course, this does not take into account, for example, that humans may be willing to understand another human making a mistake, but at least for now, they don't seem to be educated enough, for example, to understand that the machine can make a mistake, and who is responsible for the mistake. Somebody must have made a mistake if the machine made a mistake, which is already a sign of not being educated about the technology, because the technology is inherently statistical, and so it is, even if you see a mistake, because there is always a small error rate, it doesn't mean that some programmer made a mistake, right? So, but the fact that you need the time, and I don't think we are at that level, to have the society and even policymakers to understand, really being educated, that is really needed before these policymakers, for example, get to the point of being able to say, these, for this society, these are the relevant tests or thresholds or measures and so on. So the psychological effect of having this, it has to be taken into account, and it may be very dynamic. With time, it may change the attitude of a society towards a technological solution.
Yeah, actually, I imagine, there's so many levels to this. Like, on the one hand, people have usually exaggerated reactions to mistakes made by AI systems that seem extra stupid from a human standpoint. So, like Tesla drives right over a cyclist or something. And then we're more forgiving of like human mistakes in the same context. I would imagine that this is something that's been happening technologically for all time. Like, the first time a car drove over a pedestrian, something we'd now go, okay, that's awful, of course, but it will happen, might have been much more outrageous back in the early days of like Ford automobiles, that sort of thing, because it was just a new phenomenon. We just hadn't seen this class of error get made in the first place.
Yeah, but with AI, it's easier to make those mistakes. Because in some sense, if you see a stupid what you would say stupid if made by a human being. So you tend to relate to what a human being would do. And so you say, oh, that's a very stupid mistake. And in your mind, you say, oh, if the AI makes such a stupid mistake, then who knows what it would do with more complex situations, or all over the spectrum of the distribution of the data. While instead it's not that way, because the AI can solve much more complex problems much better than human beings, but still it has some of these stupid mistakes, because it reasons, not reasons, but its machinery is completely different. The way it looks at the data is completely different. So that's why you have these mistakes that you say, oh, a human being would never do that mistake. So you see, we are still with a very stupid machine, while instead is not really true. And even like a system like online translators. Yes, sometimes he makes very stupid mistakes that a human being would never do, even if you're not really into these two languages. But overall, it is very, very good quality to use those systems. And we tried to use other methods that did not have statistical analysis and so on, that were parsing the sentence and then translating and then parsing on the other side and so on, that the quality was much, much, much lower. So the fact that machines make mistake seems to be, which is also for human being, I guess, seems to be a necessary thing to be able to actually perform well in a variety of situations. Much better than a system which is more brittle and does not make mistakes, yes, but they cannot even have a good quality in many cases.
Yeah, and from that standpoint, explainable AI starts to look a lot more like empathy building for AI systems, so that at least we can understand the mistakes and we can tell ourselves a story about, oh, okay, we can patch this up so it doesn't happen next time type thing. Almost more about trust building than about actual capacity building.
Of course. Explainability is mostly about trust. Yes. Mm-hmm. It's mostly about trust and the fact that you can build these effective human-machine teams. If you don't have this relationship through explainability, then how do you build a team? How do you build even a team with another human being that behaves maybe in a correct way, makes correct decision, but never tells you why? So, okay, so it's not really a team. How can I rely on this person if he doesn't even tell me why he made those decisions, even if I see that these decisions are good ones?
Yeah, well, it's a fascinating area of inquiry, and it's so interesting how you brought together symbolic learning, the agent side, multi-agent stuff, and deep and reinforcement learning to kind of think through this whole philosophy and theory. Thanks so much for making the time for this chat. This is a lot of fun. Francesca, do you have a website that you'd like to share, or any personal blog maybe if people want to read more about your work?
I think that people can look for me on the web, and you find me on LinkedIn or I'm also on Twitter, but I'm not very active there. I'm especially active in looking at all the discussions on Twitter more than participating. They find me also on Facebook, but they also find me, on if they want to look at my research papers, they find me at DBLP, which has all my papers, or at the IBM research. My profile is there with my what I'm doing.
Fantastic. All right, we'll make sure to put a couple of those links in the bottom of the blog post that'll come with the podcast so people can check it out. Thanks so much, Francesca. I really appreciate it.
Thank you. Thank you.